I welcome you to this lecture number 3 in our course on fundamentals of transport processes. In the previous introductory lectures, I had tried to explain what it is that we will be doing and why we will be doing it. Now, in this lecture, I will try to go through how transport processes are modeled using dimensional analysis. This is the kind of thing that is done in unit operations, for example, where we take a macroscopic picture of the entire unit operation and try to find correlations between how much material, mass, heat has been transported and the conditions that are applied on the system. The temperature differences of the inlet and outlet stream, or the concentration differences, the concentrations of the different species in catalyzed reactions and so on. So, based upon those large scale properties of the system, what is the transport rates that you can expect? That is the subject of unit operations, and dimensional analysis plays a powerful role in enabling us to model these effectively. As I will show you, it reduces significantly the number of parameters that we have to vary in any experimental modeling of the system. So, last lecture I had taken you through a few different examples and shown you how transport plays an important role in those. Okay. The first of these was this reactor system, where we have a solid catalyzed reaction and there are particles on which the reaction gets catalyzed. And I had tried to explain to you that it is not sufficient to ensure that enough raw materials are put into this reactor, enough products are taken out of the reactor, there is enough heat that is supplied or taken out of the reactor. It is also necessary at the microscopic scale, at the particle scale, okay, to ensure that where the reaction takes place, there is sufficient amount of reactants being a sufficient flux of reactants to the surface locally. Okay. And this flux is determined by a variation in concentration close to the surface. Of course, once the reactant reaches the surface, it can react, and then the product of course has to come out of the surface. And it is not sufficient if you just ensure that the reactant reaches the surface, you have to also ensure that the product comes out of the surface. The conditions have to be such that there is a concentration difference of the product between the surface and the bulk of the fluid. Similarly, in the case of exothermic or endothermic reactions, it is necessary to ensure that there is sufficient flow of heat either to the catalyst surface or from the catalyst surface to ensure that the reaction takes place at the specified rates. If you do not supply heat for an endothermic reaction, then of course the temperature of the catalyst will decrease and the reaction rate will slow down. Alternatively, if you do not take out heat from an exothermic reaction, then the temperature will continuously increase, and this could lead to hot spots and runaway reactions. Now, the transport rates are enhanced by mixing in fluids, and that mixing basically transfers momentum from this impeller, okay, that is being used for mixing the fluid into the fluid. And that transport of momentum takes place due to shear stresses that are exerted at the surface of the impeller. Okay. And these are the kinds of processes that we will be studying. Similarly, in the other example that I had taken of the heat transfer in a heat exchanger, it is not sufficient to ensure that there is sufficient amount of heat coming in and going out. Okay. You also have to make sure that locally at every point there is a sufficient amount of heat being transferred across the surface, so that cumulatively when you add up all the heat that is transferred, it is sufficient to reduce the temperature of this heated fluid to the level that you specified. Okay. And we had also taken an example of a cumulative spray dryer, which includes both mass transfer and heat transfer. In this case, droplets that are ejected from a surface have to cool and dry before they hit the wall of the spray dryer. These droplets are usually contain a lot of moisture, roughly 80% in many cases, relatively small in size, about 100 microns, and as they move through the fluid, there has to be heat transferred through the droplet to evaporate all the moisture that is inside. This heat transfer evaporates the water, and that water has to be transferred out of the droplet. Okay. Both of these take place through a combination of convection and diffusion. These spray dryers are quite large in size. They could be a meter in diameter, maybe a few meters in height. They have to be large enough that the entire drying process takes place before the droplet hits the wall. And for that, what is important is what happens at the particle scale, at the droplet scale, okay, at 100 micron scale. That is where we have to focus our attention. Look at the heat transfer, the mass transfer, and to find out how long it will take for the droplet to hit the wall, we need to know what is the velocity with which the droplet moves as it moves through the fluid. And that is a problem of momentum transfer. Okay. So, now we will start looking at dimensional analysis. Okay. How are these processes carried out in unit operations? There are fundamental dimensions and there are derived quantities. Okay. The fundamental dimensions in all of these cases, by convention, these are assumed to be mass with dimension m, length with dimension L, time with dimension t. Okay. So, these are the three mechanical quantities, and then we have the thermal quantity, temperature. The dimension I will call by theta, big theta, to distinguish it from time, which has dimensions t. Okay. Then there are two others, current, amperes, and then there is a unit of light energy, which is usually written as candela. Okay. Sometimes mole is also considered a dimension. 1 mole is just 6.023 into 10 power 23 molecules. Okay. So, it is just a number. Okay. You could or you include it in as one of the fundamental dimensions, but in this particular case there is no particular need to. Okay. Now, of these fundamental quantities, we will be concerned with the first 4 in this course. Okay. Sometimes we will also deal with current, but for most of the lectures we will be dealing only with the mechanical quantities and the thermal quantities. Okay. Now, these are considered to be the fundamental dimensions. Of course, there is some subjectivity in how you choose what is fundamental and what is not. However, for the present course or for the present purposes, these are considered by universal consensus as the fundamental dimensions. Okay. These you can derive the dimensions of any other quantity. Okay. All quantities that are known to us can be written in terms of these fundamental dimensions. Okay. And that is what makes it so powerful. Okay. There is only these 6, there are no others in addition. Okay. Everything else can be derived. Okay. The velocity, for example, is the distance travelled per unit time. Okay. So, it has dimensions of length times t inverse. Okay. The acceleration is the rate of change of velocity, the velocity change in velocity per unit time. Okay. So, therefore, the acceleration is the velocity per unit time. So, this is L t to the minus 2. Okay. Force is mass times acceleration, Newton's third law. Okay. It is equal to mass times acceleration. Okay. Therefore, this will be m L t power minus 2. Okay. Work done is equal to force times distance, force moved times distance. Okay. Therefore, the work done is the force times distance, that is m L square t power minus 2. Okay. And similarly, energy also has the same dimensions as work. Okay. Energy has the same dimensions as work. Power is the energy input per unit time. Okay. Power is the energy input per unit time. So, it will have dimensions of energy divided by time. Okay. So, that is the dimensions of power. So, these are the dimensions of some common mechanical quantities. Okay. Now, we will come to dimensions of quantities that we will use in this course. Okay. Pressure is force per area. Okay. So, force has dimensions of m L t to the minus 2, and the area is length square, okay, length to the second power. Okay. Therefore, the force per unit area will have dimensions of m L inverse t power minus 2. Okay. So, that is the pressure, force exerted per unit area of a surface. Okay. The stress also has dimensions of force per unit area, okay, except that commonly pressure acts perpendicular to the surface and stress acts parallel to the surface. Okay. So, that is the only distinction, but stress as well has dimensions of m L inverse t power minus 2. Okay. Okay. Now, we often deal with the fluid density, okay, the mass per unit volume of the fluid. Okay. So, the density is an important quantity. Okay. It is written by the symbol rho. Okay. Density is mass per unit volume. Okay. Volume has dimensions of length to the minus 3 power. Okay. So, this is m L power minus 3. Okay. Concentration of a solute, okay, concentration of a solute in a solvent also has dimensions of mass per unit volume, mass of solute per unit volume of fluid. Okay. So, concentration will have the same dimensions as total densities. It also has dimensions of m L power minus 3. Okay. The difference is that the density refers to the total mass per unit volume, whereas concentration refers to the mass of a particular solute per unit volume. Okay. Now, let us come to fundamental quantities that we deal with in mass transfer. Okay. The flux of a solute. Okay. The flux is defined as the mass that is being transported across a surface. Okay. It has the symbol J. Mass transported across a surface per unit area per unit time. Okay. Flux has dimensions of mass transported across a surface of the solute per unit area per unit time. Okay. So, mass has dimensions of m, area is length square. So, I get L to the minus 2 and T to the minus 1. Okay. So, that is flux of a solute across a surface. Okay. Now, in mass transfer, okay, the other quantity that is of importance is the diffusion coefficient. Okay. How do we get the diffusion coefficient, the dimensions of the diffusion coefficient? For that, we have to use some relationship in which we know the dimensions of all quantities except for the diffusion coefficient. Okay. In this particular case, for mass transfer, that relationship is the Fick's law of diffusion. Okay. which states that if I have some volume of fluid, okay, of area A, okay, across which, okay, area A and length L, across which I apply, there is a difference in concentration delta C, okay, across which there is a difference in concentration delta C, then the flux that results will be equal to minus the diffusion coefficient times delta C by L, okay, where flux is the mass transported per unit area per unit time. Okay. So, in this we know the dimensions of everything apart from this diffusion coefficient d. Okay. So, if you look at the dimensions on the left hand side, it is mass length to the minus 2 T inverse, okay, that is equal to the dimension of this diffusion coefficient d, okay, times, okay, delta C is a concentration difference. So, it has dimensions of mass length to the minus 3, okay, it has dimensions of mass length to the minus 3, because it is a concentration difference, a difference in concentration between two locations. That has to be divided by the distance between those two locations. Okay. And from this you can see quite easily that the dimension of diffusion coefficient, okay, the mass dimension will cancel out on both sides, and this will turn out to be L square T inverse. Okay. Okay. So, the dimension of the diffusion coefficient is length square times T inverse. Okay. Now, let us go through some fundamental quantities in heat transfer. Okay. Okay. The properties of the fluid in heat transfer are the specific heat and the thermal conductivity, okay, and the flux is the heat flux. Okay. So, the heat flux Q, okay, okay, is defined as Q is equal to heat transferred per unit area per unit time. Just as J is mass transferred per unit area per unit time, Q will be the heat transfer per unit area per unit time. Okay. The heat energy has dimensions of m L square T to the minus 2, okay, that is the dimension of energy. Okay. Area is length square and time is T. Okay. So, therefore, the dimension of the heat flux will be equal to m T to the minus 3. Okay. And then we have two thermal properties, the specific heat, okay, okay, specific heat Cp, okay, and the thermal conductivity K. And the thermal conductivity K. Okay. The dimension of the specific heat. Okay. How do we get that? We know that the change in energy of a fluid is related to the specific heat by mass m Cp times delta T. Okay. Where m is the mass of the system of the fluid and delta T is the temperature difference. Okay. And in this we know the dimensions of everything except for this specific heat Cp. Okay. So, on the left hand side I have an energy, okay, m L square T power minus 2, okay, is equal to the mass m, the dimension of the specific heat, okay, times temperature, that is theta. Okay. And from this you can easily see that the dimension of specific heat is L square T power minus 2 theta inverse. Okay. Now, next is the thermal conductivity. Okay. And for the thermal conductivity, once again we need a relationship in which we know all the dimensions of all quantities apart from the thermal conductivity. Okay. The relation in this case is, of course, is Fourier's law of heat conduction. Okay. Fourier's law of heat conduction states that if I have some volume of fluid, okay, of length L, across which I have applied a temperature difference delta T, okay, then the heat flux that is going through this Q is equal to minus K delta T by L. Okay. Negative sign because heat is transferred from regions of higher temperature to regions of lower temperature. Okay. Now, in this particular relation, I know the dimensions of all quantities apart from this thermal conductivity K, and therefore, that I can find out. Okay. So, in this particular case, the dimension of Q, okay, is m T power minus 3. This is equal to the dimension of K times the dimension of temperature divided by the dimension of length. Okay. Therefore, the thermal conductivity, the expression for the thermal conductivity will turn out to be m L T power minus 3 theta inverse. Okay. So, that gives us the dimension of the specific heat, the heat flux and the thermal conductivity. Okay. And then of course, we have to come to dimensions of quantities of use in momentum transfer. Okay. In momentum transfer, the fundamental quantities are the stress, okay, and the viscosity. Okay. The stress, of course, I have already derived for you. Okay. The stress has the same dimension as the pressure. Okay. How do I get the viscosity? I need some relationship in which I know the dimensions of all quantities apart from the viscosity. Okay. And that one is, of course, Fourier's law for Newton's law for viscosity, okay, which basically states that the shear stress tau is equal to mu delta U by L. Okay. So, if I have some fluid in a gap between two plates and the plates are separated by a distance L, okay, and if I apply a velocity difference delta U between the top and the bottom plates, there will be a flow within this fluid. Okay. And the shear stress is equal to the viscosity times the velocity difference divided by the length scale. In this case, delta U by L is what is called the strain rate, okay, of the fluid. And in this case, we know the dimensions of all quantities apart from the viscosity. Okay. So, from this I can derive what is the dimension of the viscosity. Okay. So, I know that the stress in this case is m L inverse T inverse is equal to the dimension of the viscosity, okay, times dimensions of velocity L T inverse divided by the length. Okay. And from this I can derive what is the dimension of the viscosity. Mu is equal to m L inverse T inverse. Okay. So, that is the dimension of viscosity. Okay. So, these are the dimensions of some common quantities that we will use during the course. Okay. There are others, okay. For example, surface tension, for example. Okay. Okay, gamma. Okay. Surface tension is a force per unit length, okay, or energy per unit area. Okay. So, therefore, force per unit length will basically be force m L T inverse T to the minus 2 divided by length. So, this is just equal to m T to the minus 2. Okay. And these are the dimensions of the common quantities that we will use during this lecture. Okay. So, dimensional analysis simple. Okay. There are fundamental quantities and there are derived quantities. Fundamental quantities mass, length, time, temperature. Okay. Current of course and light, these are two things that we will not use very often in this course. But with just mass, length, time and temperature you can see the multiplicity of quantities that can be described, okay, all the way from velocity, acceleration, force, work, pressure, stress, flux and so on. Okay. With these fundamental quantities we can now go ahead and try to look at problems. Okay. So, the first problem that I will consider in the next lecture is the problem of a particle in a fluid that is settling under the action of gravity. Okay. Let us assume for simplicity that the particle is spherical particle with diameter d and it is moving with velocity u. Okay. Of course, on this particle it is settling because of the density difference between the particle and the external fluid. Okay. So, the force on the particle due to gravity is just equal to mass times the acceleration due to gravity. Okay. However, because the particle is translating through the fluid, this does generate a fluid flow around the particle. Okay. This does generate a fluid flow around the particle. That fluid flow results in certain frictional losses, because whenever fluids flow, more accurately whenever there is a strain rate in the fluid, there is deformation of the fluid, there is a friction due to the fluid viscosity, and that results in a force which opposes the motion of the particle. Okay. And our task will be to find out, based upon dimensional analysis, what is the force that is exerted on the particle due to the fluid flow around it. Okay. So, this one we will continue in the next lecture. I will start off with dimensional analysis for this simple problem, and then I will try to progress into more complex problems, such as the heat exchanger problem that we saw in the first two lectures, the problem of the transport from a spherical particle that we saw in the first two lectures. We will progress on to those which are a little more complex problems. So, I will see you in the next lecture.